Hi guys, I'm Zach McGill, and this is my lab video for Physics 2211 at Georgia Tech, the Choose Your Own Adventure lab. So a quick introduction, I chose to do my lab on Felix Baumgartner and the physics of falling fast. And if you didn't know, Felix Baumgartner was the man who jumped to the Earth from a helium balloon in the stratosphere on October 14, 2012. As part of the project, he set the altitude record for a manned balloon flight, a parachute jump from the highest altitude, and the greatest free fall velocity in human history. So we're going to look at the video, or kind of look at the video, of his fall, and look at the physics behind it, and then try and construct a model that determines the forces acting on Felix. And then finally, we'll spend some time talking about air resistance and the effect of air density on our problem. So first off, we're going to talk about analyzing the motion, which we first have to answer, can we? So unlike previous labs, the video of Felix' jump cannot just be shoved into Tracker and easily plotted. There's a couple reasons. The first off is there's no camera that can capture the entirety of Felix's motion. So when he jumps out of this balloon, as you can see here from the, you can see the curvature of the Earth even. He's so high up, there's no possible camera that could capture this motion. So if you guys haven't before, just please YouTube Felix Baumgartner jump, and you can see it on YouTube. It's not a video that could be useful for the lab, but it's really interesting to see. So we're going to go ahead and move on to the bVicon code. A few initial things that you can't see here. The mass of Felix in his suit is approximately 90 kilograms. The proportionality constant, which we'll get into more, it helps constantly drag force, is negative 1.3. And then the cross-sectional area of Felix that we used for this lab was 0.4 meters squared. One thing that comes up in the lab is if this number is accurate. So we can't really tell what his exact cross-sectional area is because we don't know, and also because it changes throughout the video. It could fluctuate anywhere from 0.1 meters, which is basically either feet first or head first, and 0.7 meters squared, which is if he was falling flat, that's roughly how tall he is with his suit on. So we'll go ahead and look over here at the code. It's going to look probably pretty similar to Lab 2 where we dropped a ball, because basically that's all it is Felix is a ball, but we're dropping him much faster. So here you can see while the ball's position is greater than 1, basically until he hits the ground, we have a W, which is the force of gravity. We have a velocity, which we're constantly updating. We have a drag force, which we'll talk about more later, but is this negative constant times velocity squared. And then we have an F net, which is basically the weight force, or the force of gravity pushing him down, versus the drag force pushing him back up. Of course, we update the ball's position and velocity at the end here. And in my case, I'm writing this all to a CSV file for later observation. So let's go ahead and look at that. This is a position versus time graph for Felix's fall in the first 37 seconds. So we only did the first 40-ish seconds because this is the only way you can see when he reaches terminal velocity. According to this data, he reaches terminal velocity within 5 seconds, which obviously seems a little fast, and we'll talk about why that is later, but that's just useful for you guys to see how fast he's really going. Alright, so one thing we need to talk about is the drag coefficient used in this lab. So I had to do a lot of outside research to try and figure out the drag coefficient. There's actually been a lot of physics done on this to see what a possible drag coefficient could be at that speed and at that kind of altitude. So based on the Earth's atmosphere, it could be anywhere between 0.9 and 1.3, and these values are based on existing data regarding bombs dropped at supersonic speed. Because Felix Baumgartner did reach supersonic speed for a short amount of time, that's why 1.3 was chosen, because that is typically indicative of short periods of supersonic speed, which is what occurred, obviously, with Felix. So a little further analysis. We want to know what a plausible model is for analyzing the drag force of Felix. So I used the drag force as 1/2 A, which is his cross-sectional area, V squared. So it's important to note that this is only so accurate because it does not include a change in air density. So how would a change in air density alter the results? So as you can see here, this is a graph of the density of air versus the altitude above sea level that you go, and this isn't even as high as Felix jumped from. So as you can see, the density of the air decreases by quite a bit, and this means that at those higher altitudes you can fall through the air quicker. If you think about air as not just empty space, but as something pushing back on Felix as he falls, the higher up he's going to fall faster, and then that weight force is going to increase. if I wanted to have a perfect model for the drag force, I'd need to include something about the change in air density that's pushing back up on Felix as he falls down. Alright, one last final thought. So one of the things that this lab really showed me, and could show you guys as well, is the importance of using all available constants when creating a model. So in this case, it was the air density really affected my terminal velocity, which in fact in my calculations it only took Felix 5 seconds to reach terminal velocity, when in reality that speed was reached more at 30 seconds. So it's a pretty significant difference based on really only one missing component of the lab. And then also shows the difficulty of creating a model without completely accurate data, which is kind of the same thing as I just said. Thank you guys for watching. Have a great end of the semester, and I'll see you later.